Hey everyone! Welcome back to our chemistry classroom. Today, I'm diving into a principle that's at the very heart of thermochemistry, Hess's law. By the end of this session, you'll not only know what Hess's law is, but you'll also get why it's so useful, and exactly how to use it to solve real chemistry problems. Let's kick things off with the basics. Hess's law says, the total enthalpy change for a chemical reaction is the same, no matter which route the reaction takes, as long as you start and end at the same place. In other words, it doesn't matter if your reaction happens in one giant leap or in a bunch of smaller steps. The amount of heat released or absorbed, called the enthalpy change, will always add up to the same number. This is all thanks to the law of conservation of energy, which means energy can't be created or destroyed, just changed from one form to another. So when you're looking at a chemical reaction, the total energy difference between your reactants and products only depends on their energy levels, not the path you took to get there. Let me put it this way. Imagine you're climbing a mountain. You could go straight up the steep path, or take the longer winding trail around the side. No matter which path you choose, the difference in altitude between the base and the summit is always the same. Hess's law works just like that. It's not about the journey, it's about your starting and ending points, or in chemistry terms, the reactants and the products. Let's see this in action with a classic example. Suppose you want to figure out the enthalpy change, DH, for this reaction. C, as graphite, plus O2, makes CO2. And you want to know, what's the DH? But all you actually know are these two reactions. First C, graphite, plus half O2 gives CO, with DH equals negative 110.5 kilojoules per mole. Second CO plus half O2 gives CO2, with DH equals negative 283.0 kilojoules per mole. Now, if you add these two reactions together, the CO on both sides cancels out, leaving you with C, graphite, plus O2 gives CO2, exactly what you wanted. And thanks to Hess's law, you just add the DH values negative 110.5 plus negative 283.0 equals negative 393.5 kilojoules per mole. So even though you didn't do the reaction in one step, you still found the answer. That's the power of Hess's law. Now, where is Hess's law actually useful? Sometimes the reaction you care about is too risky or just impractical to do directly. But if you have data for other related reactions, Hess's law lets you calculate the enthalpy change anyway. It's also super handy for things like heats of formation or combustion, where you can piece together values to get what you need. In advanced chemistry, like calculating lattice energies in the Born-Haber cycle, Hess's law is your go-to tool for figuring out energy changes you can't measure directly. Think of it as chemical bookkeeping for energy. So the big takeaway? Hess's law proves energy is a state function. It only cares about where you start and finish, not the path you take. It lets chemists calculate tricky energy changes by breaking things down into simple steps with known enthalpy values. Thanks for hanging out and learning about Hess's law with me. If this video helped you out, hit that like button and subscribe for more cool chemistry content. Got questions or want more examples? Leave a comment below and keep that curiosity burning bright.